Good morning, this is VLSI Data Conversion Circuits, lecture 40. So far we have seen how to design a continuous time delta sigma loop, that is how one finds the loop filter coefficients, how one scales them for proper swings, how one can go and realize integrators which are basically the main parts of the loop filter, right. The next thing to do is to look at the quantizer part. The quantizer, as we all know, consists of the A to D and the D to A converter. So today we will start looking at the A to D converter, right. So since a delta sigma loop is basically a feedback based structure, the kind of architecture that you would use for the A to D converter is the one which has the least amount of delay, right. So there are several ways of realizing A to D conversion, you all know that, and some of them can be very hardware efficient, but then will take a long time, and that makes sense because basically if you are hardware efficient you need to accomplish a task, so you keep reusing the hardware again and again, right, which means that it will take a long time to accomplish the conversion, right. On the other hand, if you want to do everything very quickly, it means that you pay a price in terms of the extra hardware required. When you want to do things quickly, what you would do would be to work in parallel, right, and once you do things in parallel, it means that usually you waste a lot of resources, in the sense that you are doing redundant things with much of the hardware, but that is the price you pay for speed, right. So the considerations for the ADC in the sigma delta loop must be low latency, and thankfully this is not too much of a problem, right, as we will see going forward, and the basic idea is to therefore use the family of converters which work the fastest, and these are called flash A to D converters. Flash A to D conversion is not just restricted to use in delta sigma loops, okay. It happens to be the best choice in a sigma delta loop simply from the point of view of speed. Flash converters are also used in other systems where feedback is involved, okay, to close some kind of loop, and in such cases the latency of a converter has to be as small as possible, and this is what motivates the use of a flash converter. Now the basic idea behind a flash converter is very straightforward. What is the A to D converter basically trying to do? It is trying to compare the analog input to a set of levels, right. The simplest or the most straightforward way of doing this would be to have a basic building block called a comparator, which in principle gives an output D, where D is a logical 1 if V in is greater than V ref, and is a logical 0 if V in is less than V ref, right. Now V ref is the so called threshold of the comparator, okay. Now since the flash is basically trying to compare an analog input against a bunch of levels, a straightforward implementation would be to say I will have an array of comparators. For example, for a 3-bit flash, one would want to classify the input into 8 bins. So, how many thresholds would be needed? You will need 7 thresholds, right. So, in general, for an n bit flash you will need 2 to the n minus 1 thresholds, which is equivalent to so many comparators. Okay. And you have 8 of these guys or 7 of these guys. The input is common to all these comparators. All right. And the references go from V max by 8 to 2 V max by 8 all the way to 7 V max by 8. This is V. Okay. And you therefore get a code at the output which is what you get at the output is basically a string of 1s followed by a string of 0s, right, depending on the location of the input, right. And how many bits are there here? I mean, how many lines are there here? In general 7, which is 2 to the 3 minus 1, all right. So, as you can see, if the input lies say between the 6th and the 7th comparator, right, all the comparators below the input will read a 1 and all the comparators above the input will read a 0. So, if everything is working properly, then this code, which is 2 to the n minus 1 bits long, consists of string of 1s followed by a string of zeros, and this is given a special name, right. Depending on the level of the input, the number of 1s keeps varying, just like the mercury in a thermometer, and this is why this code is called a thermometer code. All right. Now, the thermometer code is somewhat of a special code in the sense that even though you have 2 to the n minus 1 bits, all possible sequences are not allowed, only those special sequences which are all 1s followed by all zeros are allowed. and you can see clearly the redundancy already present, because in principle if we know that this comparator is showing a 1, it means that the input is higher than 6 Vmax by 8. There is in principle no need for us to look any further below. If it is less than, if it is greater than 6 Vmax by 8, it automatically follows that it is greater than 5 Vmax by 8 and all the way up to Vmax by 8. However, there is no time for all that, so we decide to do, we compare it with all the thresholds anyway. That is why you are wasting hardware, right. So in principle the what really you care about is the transition between the all ones and the all zeros, and in principle all the comparators above this one and all the comparators below this one are basically redundant as far as simply figuring out what the input is. You understand? So that explains why a flash converter is fast, and also explains why it is within quotes very wasteful of hardware. So it is naturally only used in applications where A, latency is paramount, and B, where the hardware complexity is modest. So if you want to do a regular standard flash, you can see that every time you increase the resolution by 1 bit, the number of comparators actually doubles. So the hardware complexity goes exponentially as the number of bits. Is this clear? So typically 6 bits is a break even point for standalone flash converters, okay, because there are several difficulties associated with increasing the number of comparators beyond about 64, which is what you will need for a 6-bit converter, okay. Somebody has to drive the flash, right, and as we know, usually you would like to sample and hold the input and then work off that sample, that is what you are trying to quantize, you understand. So what happens is that the circuitry which drives the array of comparators has to now drive a larger and larger load the moment the number of comparators keep increasing, alright. So for standalone flash converters, typically 6 bits is a break even point. Beyond that, people try and see either explore ways of avoiding the flash converter, right, or try simply some innovative techniques to try and keep the number of comparators low while still giving the resolution you want, maybe 7 bits or 8 bits, okay. But standard flashes are usually limited to about 6 bits, as you will find out if you just browse the literature. Now as in the particular case of a delta sigma loop, driving a big flash array costs a lot of power, because the loop filter is driving the array of comparators, isn't it. In a flash converter, at a pinch you can say, oh, well, I am only designing the comparator array, I do not really care about who is driving the array, so it is not my problem, so I have 6 bits. But in a delta sigma loop, the same guy is probably designing the flash as well as the loop filter, which means that the array of comparators has to be driven by the loop filter, which is being designed by the same person. So you are now doubly careful, because if you try and make life easy as far as the sigma delta loop is concerned by choosing a large resolution for the flash, then driving it becomes a problem and causes, if you drive a larger capacitance for the same power, it means that it will take a longer time, right. So is associated with not only the hardware complexity of a 6-bit converter, but also the delay and drive needed to drive such an animal, okay. So in sigma delta loops, typically people have restricted themselves to 4 bits, okay, again as you will find upon perusing the literature. So 4 bit seems like a reasonable trade off between the benefits offered by multi-bit modulation, right, which are a increase in the maximum stable amplitude for a given noise transfer function, right, or you can make the more the resolution of the quantizer, the larger you can make the out of band gain of the noise transfer function, thereby reducing the in band noise. 2, the if you use an NRZ type feedback DAC, the effect of jitter is greatly reduced if you use a multi-bit modulator as you keep increasing the resolution of the quantizer, right. On the other hand, doing the quantizer itself becomes more and more difficult as you keep increasing the number of levels. So, a reasonable pain point beyond which the benefits offered by multi-bit quantization, right, are overweighed by the hardware complexity involved in making the quantizer itself, right, restrict the number of bits to about 4. Now, the output of the flash needs to be a binary code finally, right, between, in this particular example, 000 through 111, but what we have at the output of the comparator array is a 2 to the n minus 1 bit code, which is a thermometer code. So, to figure out which bin the input lies in, what we are interested in is figuring out the transition between the all 1 and the all 0, right. So, that is again very straightforward, simply because in principle what you can do is to find the transition okay. So, right, so this becomes all right. So, this becomes D7, okay, the 7th decision of the 7th comparator, D6, D5, etc., and all the way up to okay. All right, and I think it's okay. Sorry. All right. So, this must always be a 1. Okay. So, how many will be there now? No, 8. Okay. So, this is the digital hardware required to determine whether, I mean where the transition occurs between the all zeros and the all ones. Okay, as you can see, it is very straightforward, there is nothing to it. The properties of this code are there is only of these 2 to the n wires coming out, only one of them will be high, all the others will be low, and this is often called, even though it is 1 of 2 to the n, it is actually called the 1 of n code. Okay. So, this is called the output of the thermometer comparator array is the thermometer code, and the output of the transition detection is the, in this particular example you will get a 1 here and all else will be 0. This is the 1 of encode. All right. Now, we need to find from this 1 of encode you have to generate a binary word, right, which is 3 bits long. So, what is the easiest way you think of generating the binary output? Use an encoder, right. So, this goes into an encoder, right, and the output of the encoder is a 3 bit word. Is this clear? All right. So, in the early flash converters what would happen would be that the comparator array would by itself be driven by the analog input, not by a sampled and held input, okay, and the comparators would implicitly have the sampling operation in them, okay. In other words, the comparators would not be something which compare the analog waveform with reference and then sample. They would be inherently, the comparators would be what are called sampling comparators, as opposed to continuous time comparators where the output at all times is supposed to be signum of input minus reference. You understand? When we see the circuits you will appreciate this point a little better. So, the comparators used to have implicit sampling, and that meant, especially when the number of comparators was large, you would find that you had to propagate the clock, right. The sampling clock would be responsible obviously for the comparator sampling, and when you physically lay out these transistors, because of the large number of comparators which would be laid out as an array, right, the clock which is responsible for sampling would have to travel from one end of the array to the other end of the array. So, nominally all the comparators are supposed to be working off the same input, right, but now if the clock is delayed across the array, then what happens is that in effect different comparators are making decisions on inputs which are at different times, right. Granted that this difference in time is small, but in principle all these comparators are making, which are supposed to be making a decision on the same input, are in reality making decisions on inputs which are slightly displaced from each other in time. Now, this is not an issue when the input is varying slowly, but remember the whole idea in having a flash is to be able to sample really fast, which also means that the input signal is likely to be fast. So, now since the input is different comparators are actually digitizing slightly different inputs, okay, one used to often end up with a situation where the thermometer here would not be a pure thermometer, I mean ideally you are expecting a string of 1s followed by a string of zeros, right. In practice what one would observe would be the ideal let us say you are expecting something like this, right. Actual code the lack of a sample and hold, right, would perhaps look like this, simply because these comparators here are not looking at the same signal, right. You can always come up with a signal which will give you this kind of thermometer output, simply because all the thermometers are not all the comparators are not digitizing the same input, and this is happening because of two things. One, there is no sample and hold, right. If there was a sample and hold, what do you think will happen? Okay, so let us say this is the input and there is clock skew. So, for instance, this would be say the sampling edge at comparator 1, and because of clock skew effects this would be perhaps the sampling edge of comparator n, alright. So, the first comparator is actually digitizing this point, the last comparator is making a decision on that point, and the comparators in the middle are actually comparing something in the middle to their references. So, since all these comparators are not working off the same input, right, there is a possibility, this is actually a distinct possibility. Now, this is happening because A, lack of a sample and hold, and B, because of clock skew. Right. Clock skew is something which is fundamental and you cannot avoid it, because finally all these comparators cannot be in the same place, they will be physically placed apart, which means that any clock that you run to these comparators will have a skew between the first and the last one, right. So, how do you think having a sample and hold upfront solve this problem? Pardon?
Less than one clock cycle, the skew will be same, right?
The skew is definitely, at least you are hoping that it will be much smaller than a clock cycle.
Because the signal is held constant over that period.
That is all, right. So, the problem as you can see is that the signal is changing within this interval. If you make it stay constant, the fact that you have clock skew does not really matter. Of course, you have reduced amount of time, okay, to make a decision, but the slope is 0, therefore, all the comparators are seeing the same input, alright. So, having a sample and hold helps significantly in that way. So, a lot of the earlier flashes where there would not be a sample and hold up front, the performance would be okay for low speed inputs or low frequency inputs, but as the input frequency went on becoming higher and higher and got closer to Nyquist, you would see that the performance would degrade very rapidly, and the reason would be things like this, okay. So, the moment you add a sample and hold up front, that problem is addressed simply because once the sample is held, it is flat with respect to time, which means that all the current, I mean all the comparators see the same input. Okay. Now, in the earlier days therefore, there would be situations like this, where since neighboring comparators are not really seeing the same input, you would get not a string of 1s followed by a string of zeros, but artifacts like this, and these were called either sparkles or bubbles. In the thermometer code. Okay. I mean clearly there is a problem, right. The problem is what? I mean in principle we do not know whether the input is here or here. Okay. So, if you just use the standard hardware, then after doing the 1 of n code you will get 2 1s, and that will go into the encoder, and the encoder will give you complete garbage, right. So, this these bubbles or sparkles is a problem. While we do not know what the true input is, at least one thing we would like to make sure is that we know that the input is in the neighborhood of this. Okay. So, the final code that we get must not be wildly off from this neighborhood, okay, and that can be only ensured when only one line of the encoder is 1. If the encoder, I mean if the encoder input is a true 1 of n code, okay, then only one row of that encoder is held high, which means that even if the true, I mean decision is wrong, we are only off by a little bit, maybe an LSB or 2, whereas if 2 lines of the encoder are asserted high, then the output could be catastrophically off. You understand? So, the key point is to make sure that only the output of the 1 of n code is truly 1 of n, right, which means that at the input of the 1 of n coding logic there must be a true thermometer, only then you will have only one transition. Okay. So, what do you suggest we could do to fix the problem? What is the priority encoder? What do you do? What is highest one? Oh well, see one thing you must be aware of is that anything you do here must be modular. One of the nice things about the flash, as you can see, is that the entire logic all the way up to the encoder is copy and paste of the same basic unit, right. Now, trying to do a priority encoder, right, I suppose you could do it, okay, but I mean is there anything else that you can think of? No, no, what are you trying to do?
Externally the error, then you can't get the result.
What we ensure that the neighboring bits are, I mean, without neighboring bits are, even if the neighboring bits are, I mean, 1 zeros and transitioning, the input of the encoder has only one transition.
Yes, correct. So, how do you ensure that?
Assuming that only the neighboring bits will be,
Yeah.
then you can again add the, I mean, to each one.
Okay. Yeah. So, basically the idea is to say, okay, now I am not the input to the transition detector, I am not going to give the actual thermometer code I get, because it could be in error because of bubbles or sparkles. What I will do is I will fix the thermometer code so that it is a true thermometer, and one way of doing that is to say the output of this particular comparator is not going to be just the output of this comparator itself, but I am going to look at my neighbors and give out a majority, right. For example, if I do a majority of 3, majority can't be of 2, right, you would have an odd number of comparators, and if I did a majority of 3, that means that for this particular comparator, for instance, the upper one is 1, the lower one is 1. So, I can say without any ambiguity that this is indeed a 1. Similarly, if I assume that the lowest one is always a 1, then this will give me a 1, and what will happen here, this will also give me a 1, this will also give me a, yes, it will give a 1. What happens here? Majority of 3, where the 3 are the present comparator, the one above and the one below. So, it will give you a 1. What about this? It will give you a 0, okay, 0 and 0, alright. So, this is what is called majority of 3, and this can correct one bubble. Alright. Of course, one can say if I do majority of 5, for instance, I can correct 2 bubbles, alright, but majority of 5 is a lot more messy than majority of 3. Majority of 3 means that physically one has to only talk to find the majority output decision, one only has to talk to the decision above and the decision below. So, routing signals becomes much easier. Now, if you do majority of 5, you have to not only talk to one person below, you have to talk to the second person below as well as the second person above, which makes the whole thing very messy, and you are hoping that the probability of 2 bubbles is much smaller than the probability of 1 bubble. Okay. So, what is there here between the actual thermometer code and the one that goes to the transition detect logic is basically a majority detection logic whose job is to correct bubbles. Okay. So, this is basically what is involved in a flash converter, and therefore, the latency of the flash converter consists of the amount of time the comparators take to make a decision plus some logic delay associated with the bubble correction, the transition detect and the encoder, and you are hoping that all this is done as soon as possible, right. At least architecturally there is no deliberate delay in the whole signal chain. Okay. So, the generic block diagram of a flash converter will therefore look like this. As we just discussed, there will be a sample and hold up front or a track and hold, where the job of the track and hold is to hold the analog input to a constant value, and the advantage of this is that now in spite of clock skew which is bound to be there, all the comparators will see the same input because the input is held, therefore its derivative is 0, correct. So you have the comparator array, okay. Then it goes to the bubble correction logic, then it goes to the transition detect, so here you hope to get a thermometer code, here you hope to get a 1 of n code, and then you go to the encoder and you get the n bits out. Here it will be 2 to the n bits, 2 to the n bits, 2 to the n bits. Pardon? No, you need to add the extra, there is one here and then one on top, right? Okay. All right, and all these have to be controlled by clocks. And for example, as we have already seen long ago, the sample and hold you need non overlapping clocks and perhaps boosted ones and so on. So you can't expect all those myriad clocks to be given to you from the outside. So all you will get is a single clock, and from this single clock, master clock, you have to generate all the other clock waveforms that you need, right. So this will go to various places on the chip. Yes.
Sir, in this case we are using the sample and hold, so the bubble correction logic is
Yeah.
not
So if you use a sample and hold, strictly a bubble correction logic is not necessary because the output is held, right. I mean a lot of, I mean this is a so, but still people just use a majority of 3 bubble detection, bubble correction, right, simply because it gives you, it's like buying insurance, right. You hope that there is no bubble, right, and but it does not cost too much anyway, it's so you just have it, right. So strictly what he is saying is right. Strictly if you have a good sample and hold, there should be no need to have bubble correction logic. Okay, is this clear? So this is the generic block diagram of a flash A to D converter. This is often what is called the digital backend. Alright, and the design of these is actually quite straightforward. I mean, it's just logic design. There is nothing much to it. And the key point, as you noticed in the flash, is speed, and therefore you would like all these things to be as modular as possible, and the way we have done the logic, it is definitely so. So the design procedure would be to make the logic, I mean design one slice of this entire path carefully, which is, slice means comparator, that portion involved with the bubble correction transition detect and the encoder part carefully, then just copy and paste this 2 to the n minus 1 times, right. So, you are able to now get the entire flash AD converter. Once you have done all that, you must go and then design the sample and hold to be able to drive the input capacitance of the comparator array. The input is not truly a capacitance, as we will see going forward. It can have all sorts of strange issues associated with kickback and things like that, but this is how the design would proceed. So, the key analog building blocks are obviously the sample and hold and the comparators, okay. And before I proceed, one thing I would like to point out is that the comparator array needs a bunch of references, right. Can you think of a straightforward way of generating these resistance, I mean of this reference? Yes. So, reference generation is commonly done, though not necessarily this way, but is commonly done using so V max by 8, 7 V max by 8. So, reference generation commonly done using a resistor string. So, if the resistors for instance vary across the die, and please note that the flash array is physically a big thing. So, the resistors also have to be, the resistor string has to go from one end of the array to the other. So, if there is a gradient of resistance along the die, it means that these resistors are all not identical, and there is a gradient in these resistors, which will then boil down to DNL and INL in the converter, even if the comparators were ideal. You understand? So, one thing you must understand, you must be aware of is that process gradients can cause DNL and INL due to of course, the resistors are also mismatched statistically, and this means that you will get some small amount of DNL INL anyway. Okay. All right. So, in the next class we will take a look at how to design and what all one could do to design the comparator. We saw that the comparator is the key building block of the flash, right. So, we need to be able to figure out what all ways are there of taking a voltage, comparing it with the reference, and making a digital decision, a logic decision as to whether the input is smaller than the reference or larger than the reference.